Okay, good morning, quantum enthusiasts. Today I'm very happy and excited because my least favorite number is going to fade away into obscurity. That's √1/2 today, because we're going to talk all about the Hadamard instruction. And we're mostly going to talk about the Hadamard instruction today. It's the most important instruction in quantum computing. And we'll get like a new perspective on it. We'll come to like it even more than we used to like it, which is great. And, this lecture is maybe the last lecture, at least for a while, where we kind of like go over the basics of how things work in quantum. And, in starting probably the next lecture, we're going to try to like actually do some stuff, like maybe do some new kind of algorithm or something, some real programming. But today we'll, get the footing all set up, and we'll also get a little bit back to mystery toggles, and we'll see what was going on there. We probably won't see, we won't see why it works, but maybe we'll at least see how it's working. Okay, so we were a little bit in the middle of something last time we were talking. We were talking about this thing, this unitary property. This is a special property that you didn't know all the instructions, the pseudocode instructions had. But it does. But they do. That was a terrible sentence. Anyway, so unitary property is a property that, let's say, a hypothetical instruction, let's say given by its matrix, may or may not have. And what is the property? The property is that, it's quite magical that whenever you put into it a quantum state that's a valid state in the sense that the sum of the squares of the amplitudes is 1, and then you do the operation, the resulting state will also have sum of squares of amplitudes 1. And we saw last time, actually, that all the classical reversible operations have this property, and they kind of have it for like a pretty reasonable reason. They just shuffle the amplitudes around, which doesn't change the sum of the squares of the amplitudes. But Hadamard also has this property, and, today we'll start by seeing why that's true. The reason we're interested in this property is this law of quantum mechanics, which basically says the candidate, instructions, the candidate matrices or path diagrams that have the unitary properties are exactly those transformations that are physically possible in the world. Okay, so the legal quantum operations, or the ones that you can program, are all the ones that have this unitary property, which they kind of have to have because, the laws of quantum mechanics say, the state of a system always has sum of squared of amplitudes 1, so your transformations better preserve this property. Okay, so what we're going to do now is check that, we want to check that all the programs we ever build up from the pseudocode instructions have this property. So it's enough to check that the basic instructions have this property, and we checked it for all the classical reversible ones. So we really just need to check it now for Hadamard, which is like the main superposition creating one. I mean, we should also check it for maybe clockwise and counterclockwise and these controlled Hadamard instructions that were basically just in there for illustrative purposes, but I'll leave that basically to you, and we'll focus on Hadamard. So let's try to answer now, why does Hadamard operation have this property? So first of all, let's remember the matrix for Hadamard looks like this. Well, this is the paths diagram, but a paths diagram is just the same thing as a matrix drawn in a different way. So it maps 0 to 0 with amplitude √1/2. It maps 0 to 1 with amplitude √1/2. It maps 1 to 0 with amplitude √1/2. And it maps 1 to 1 with amplitude √-1/2. Well, you can see why it's sort of annoying to draw these diagrams, and eventually people just put the labels into a box and write a matrix instead. Okay, so we want to check that you have this property, this unitary property. So we'll just do the obvious check. So let's say you have one qubit A, and it's in this state. X amplitude on basic state 0. And Y amplitude on basic state 1. Okay, and X and Y could be any two numbers whose squares add up to 1. Okay, and then you do Hadamard. We want to check that the resulting state also has the sum of the squares of its amplitudes equal to 1. So, we got to find out what is the sum of the squares of the amplitudes when we do the Hadamard instruction. So let's calculate that, for which we use, some amplitude tree. So, the incoming state is like x amplitude on 0 and y amplitude on 1. So basically, you can just sort of pretend that like there was some hypothetical amplitude tree up here that did some stuff and eventually got you to 0 with amplitude x and got you to 1 with amplitude y. Okay? Maybe you did some code and this was the end of it, but now we're going to like add Hadamard A on the end. So how do you add Hadamard A on the end? Well, you just continue the tree. And like basically, this is the rule that you use to continue the tree. So you say to yourself, all right, if I'm at 0, then with amplitude root a half, I go to 0. Amplitude root a half, I go to 1. And if I'm at 1, then with amplitude root a half, I go to 0. And with amplitude minus root a half, I go to 1. Okay, and therefore, sort of the final amplitude outcomes here we get by this path product rule. So that's root a half x, root a half y, root a half y, and minus root a half y. Okay, and then we're not really done because, yeah? Oh, thank you, yeah. Yeah, please just instantly correct me as soon as I turn around. Okay, so we're not fully done because we have to do this collation or this summing. So like the total amplitude on 0 is this piece plus this piece, and the total amplitude on 1 is this piece plus this piece. So let's write this over here. So the new amplitude on 0 is root a half x plus root a half y. Okay, so I'll just factor out the root a half, my least favorite quantity. It's root a half times x plus y. And what is the new amplitude on 1? Okay, well, it's root a half x minus root a half y. Okay, which is root a half, times x minus y. Okay, and really want you to remember like this. Because this is like actually a shortcut when you're doing computations. And like this is the way you should get to know Hadamard a little bit better actually. Instead of focusing on like, what does Hadamard like do to 0 and 1, like focus on like how much comes into 0, 1. So like wherever you were, if you had amplitudes x and y, the new amplitude is on 0 is this, and the new amplitude on 1 is that. And I even like to think of this as like a little slogan for Hadamard, which is kind of that like 0 gets the sum, x plus y, and 1 gets the difference, x minus y. And then there's like the stupid part, and you stupid, okay, I won't slander it on the board in words, but like you multiply by square root a half. Okay, so this is kind of like the rule or the slogan how you can do this like Hadamard computation a little bit more quickly. And we're going to come back to this later. Okay, so we have the new amplitudes, and we should check that their squares add up to 1. That was the purpose of this digression. Although actually, since it's here on the board, let me just say for the people who are doing the homework and who love linear algebra, I don't know if you noticed, but what we're secretly doing in this computation, this picture is literally the same as this matrix vector multiplication. We're literally computing this. Well, it equals this, and this. Okay, but you don't need to use matrices in linear algebra if you don't want to. Just you can think of these like amplitude trees. Okay, so right, so we're trying to finish this calculation. So the last thing we better do is check what are the squares of these amplitudes, and hopefully it'll be 1. So let's check that. Well, I'll check it down here. Okay, so the new total squared amplitude Okay, well, if we square this, then we get like a half times the square of this, and similarly, so we get a half times x plus y squared. If we square this, we get a half times x minus y squared. Okay, I guess we can factor out the halves again. Half x squared plus 2xy plus y squared plus the square of this, x squared minus 2xy plus y squared. Okay, these cancel. We get 2x squared, 2y squared, but times a half. So that's x squared plus y squared. And that's a check mark. So why is it a check mark? Well, we assumed that the input state was valid, which means x squared plus y squared equals 1. And the new total squared amplitude is x squared plus y squared, which is also 1. Okay, so it has the unitary property. And you should even maybe a little bit remember in the back of your mind, because it's going to come up, like, if x squared plus y squared didn't equal 1, well, anyway, this number would still be x squared plus y squared. Okay, any question about this? So let me just say as an exercise for you, you can remember this funny instruction that we mentioned earlier called clockwise. We literally only cooked it up sort of to have another 1-qubit operation to talk about besides just Hadamard. But it had this paths diagram or matrix. 0 goes to 1. Honestly, I have to check my notes. 0.8 minus 0.6, 0.6, 0.8. And, if you get bored while I'm talking, you should also check that this thing has the unitary property by the same methodology. Uh-huh. Oh, yeah, this is terrible. Thank you. It's a little early in the morning. Thanks. That stays 1, 0. Okay, great. And let me also add that, you might be like, hey, how can I tell if a matrix is going to have the unitary property? I mean, especially if it's like a 4x4 matrix because it's a 2-qubit instruction, or like an 8x8 matrix because it's a 3-qubit instruction. Well, in some sense, it's like kind of a magical property, and there's not really a shorter shortcut than just literally doing this. Like just being like, okay, let's hypothetically say the amplitudes are x, y, z, and w. Let's multiply everything out and check that the sum of the squares of the amplitudes turns out to be, well, it will turn out to be x squared plus y squared plus z squared plus w squared if it's unitary. But maybe on the next homework, I'll show you like a shortcut. It's actually not even a shortcut. It's like a long cut, but it helps you conceptually understand this unitary property a bit. Turns out an operation is unitary, like a hypothetical operation that could be a valid quantum operation is unitary if when you reverse all the arrows and thereby getting like a new hypothetical operation, if this new hypothetical operation is the undo of this one, then they're both unitary. But you'll check that on the homework. And in particular, that implies that all unitary operations, all the valid quantum transformations, have an undo, which is something we check for the classical reversible operations. They're all undoable. It's also true for all quantum operations. So like the undo of Hadamard is itself, the undo of clockwise is this counterclockwise.